In this video, we're going to look at multiplying polynomials. And we're going to do this in a way, something called the area model. Before we get into what the area model is, though, we are going to review some basic multiplication just to kind of show you how the area model is structured. So we're going to start with a problem like this. We have 16 times 24. Now 16 we can break down into a 10 and a 6, and 24 we can break down to 20 and 4. The idea of the area model is we're going to break this down into smaller components and then put like components together. So essentially what we're going to do is we're going to look at the row and column and match up the components that are there. So a 20 and a 10, I can multiply those, and that gives me 200. I'm going to do the same thing in this row here. 4 times 10 is going to give me 40. This row and column, 20 times 6, gives me 120. And then this row and column together would give me 4 times 6, which is 24. And then I'm going to add them together. So when I add 200 and 120, I get 320. And if I add 40 and 24, we get 64. Now this structure looks very similar to when we looked at two-way tables earlier in the year. Same kind of idea. When I put my like terms together here, I get 384 for my final answer. Now you probably learned how to do 16 by 24 like this. 24. And 4 times 6 is 24, carry the 2, and so on. It's the same idea, except we're just breaking it down into components. And that's what we're going to be looking at today with the area model. So the area model basically says that if we have variable expressions, we can go ahead and we can distribute numbers through. And that's essentially what we're doing is distributing. So let's start with some basic ones where we're actually going to distribute using the distributive property, but show it in the area model sense. So if we have the problem 2 times the quantity b plus 7, we know from before that essentially what we're going to do is take the 2 times the b and 2 times 7, and that's going to give us 2b plus 14. But we can set this up using the area model to make it a little bit easier to organize the information. That's really the purpose of this, is to help organize the information. So we're going to take 2 times b. So this 2 is going to go right here in this box, and then the b and the 7 are going to go here. They're separate terms, so we're going to go ahead and separate those out. When I take 2 times b, I get 2b, and 2 times 7 is going to be 14. So together, these components right here make my answer, 2b plus 14. So that's just going to get copied up there. It's the same thing on this problem right here. We have 9 times the quantity a plus b minus 2. Instead of 2 terms, the 9 is being distributed to. Now we have 3. All right, so we put the 9 in that single box, and then we have a, b, and negative 2 in that box. So we can look at the like components, 9a, 9b, and negative 18. And so then our final answer is what is in here, 9a plus 9b minus 18. We can do the same with variables. So if we have a problem like this, x times the quantity 2x plus 3, when we're distributing, when we're multiplying x times x, and let's just kind of get into what that actually means. So let's just say that was a 3. So if I did 3 times 3, I know that's 9, but there's another way that I can think of 9, or 3 times 3, and that's 3 squared. Now that's knowing that x is 3. It'll work for any number, 4 times 4, 5 times 5. It's the same idea. But if we had a number x, if we did x times x, that would give us x squared. I think back to when we did radicals, our idea was that we wanted to multiply the numbers that were outside first, the coefficients we call them, and then we multiplied the other part of it. In that case, it was the radicand. Here we're talking about the variables. So this x right here is actually a 1x. So if I multiply 1x times 2x, I'm going to get 2x squared, because x times x is x squared. And then I can multiply 1x times 3 to give me 3x. So again, my final answer is what's in the box here, 2x squared plus 3x. And those are not like terms because they don't have the same exponent on the variable. That's a very important point as we move forward, that we have to know that. So that's some basic stuff right there with the distributing. Let's look at another one with a variable. Let's do a kind of a challenging one here. Let's pick this one here, 8b. So this it's not set up for us, we're going to set it up. So the 3x is alone, so we're going to put that in an isolated box. X squared, 2x, and 7, those are our 3 terms here. So we've got an x squared, a 2x, and a 7. So when we multiply those, again, our coefficient on any variable that doesn't have a number in front is 1. So x squared is just 1x squared. 3x times 1x squared is 3x to the third. 3x times 2x, 3 times 2 is 6. X times x is x squared. And then 3x times 7 is 21, so 21x. Final answer, 3x to the third plus 6x squared plus 21x. And so far, I probably haven't convinced you that the area model is this awesome, wonderful thing that we need, because we've just been distributing. So nothing really earth-shattering yet. But what we are going to get into is multiplying binomials a binomial times a binomial. So that means two terms. This is where I think the area model really shows that its value, because it helps us organize information a little bit better. So let's say we have this problem here, number 3, x plus 3 times x plus 3. Essentially what we're going to do is we're going to multiply all those boxes, just like we did on that warm-up problem where we had the multiplication of two-digit numbers. We're going to do the same thing here, but with the binomials. So I'm looking at the boxes and trying to put them together. An x and an x is going to give me an x squared when I multiply together. An x times a 3 is a 3x, and an x times a 3 is 3x, and 3 times 3 is going to give me 9. Now, I can just write all that down, and I'm not going to be right, because the next thing I have to do is look to combine like terms. So these terms right here, the 3x and the 3x, are like terms. Both of them have the same variable and the same exponent. Just so happens they're both 3's as well. That's just a coincidence. So now I'm going to put the numbers in there. I've got x squared. The 3 x's together will give me 6x, and then plus 9. Let's look at number 6, a very similar type of structure. Or actually, let's look at number 4. I kind of like that one. Number 4, we have 6 plus 5x times x plus 2. Again, the area model is already set up for us, so we're going to go ahead and use it. So 6 times x is 6x. 5x times x is 5x squared. 6 times 2 gives me 12. And 5x times 2 would be 10x. I'm looking for like terms. My like terms are 6x and 10x. So when I put those together, I'm going to get 16. Now here's where I'm going to vary a little bit on. We just kind of pick that first box, and we're going to make sure we have the highest degree exponent. What I mean by that is which one has the highest exponent. So the second is the highest exponent. That's my first term. And you'll see when we get to the factoring section next why we want to put these in what's called descending order, highest degree first. Then we're going to put these together. The 10 and the 6 we already said is 16. And then we've got this plus 12. All right, and so that's our multiplication of that using the area model. And we can extend that using binomials times trinomials. We can multiply anything together. Just a matter of how many terms are we going to get. So in number 7, we have x times x squared. That's going to be x to the third. X times 3, x squared is, 3 times x squared is 3x squared, if I can write that correctly. There we go. All right, and then x times x is x squared. This will give us 3x, negative 3x, and negative 9. So I'm looking to put my like terms together. So I have like terms here. 3x squared and 1x squared are like terms. And, I don't know why it did that. Let's try that again. So that's 3x. So let me grab my other highlighter here. Let's use the purple one. 3x and negative 3x. Now what will happen with those is they'll cancel out because they're same number but different signs. So they're going to cancel each other out. I've got x to the third. 3x squared and 1x squared is 4x squared. 3x and negative 3x is 0x, so I don't need to write it. I can if I want. I'm not going to, though, because it's not necessary. And then we have the negative 9. So again, the area model works when you have a binomial times a binomial, a trinomial times a trinomial, one terms times two terms, a lot of different approaches to it. And you'll see later that when we get to factoring, we really want to at least start off with that area model concept because it helps us to organize that information. And even in the future, you're going to see you can actually use division with polynomials with the area model.